Hello, everyone, and welcome to my talk on duck typing and type erasure in C++. Shout out to those of you who made it here after the lightning talks last night. It took me a lot of energy to get out of bed today, so I'm sure it was the same for a couple of you guys here. All right, since I'm likely a new face, a bit about me. I'm a C++ software engineer at Maven Securities, which is a high-frequency options market-making firm. We have offices in Chicago, London, and Amsterdam. So if you're curious about the space, feel free to reach out. And this is my first talk at CppCon, so I'm quite excited about it. All right. Overview of the talk before we start. So this talk is going to be about the fundamentals of type erasure, how type erasure works under the hood. Specifically, I'm going to be focusing on std function for most part of the talk. Why we need like a type erase component like std function, how a std function works under the hood. But all of this can be extended to creating your own type erase classes. It's not specific to std function at all. Then I'm going to talk about the specific implementation that I'm going to show what the runtime cost of that implementation is. And briefly at the end, I'm going to talk about std any and another approach to type erasure. A different approach to type erasure that addresses some of the runtime costs. And at the end, if you have some time, I have some bonus slides about shared type erasure and shared pointer. So with that, let's get started. Consider this extremely high-level overview of a trading system. We have an exchange on the left side. The exchange provides market data. And then we have two different trading applications. These are like two different, same binary, but like two different instances of the same trading application. One of them, say, is trading S&P 500, while the other one is trading commodities, so different set of instruments. Now, the goal is that we want this market data subscriber class to be a common concrete class, but filter out different instruments. So, like, the client should be able to pass a callback to this class upon construction and provide a filter function for the instruments. So it's a common class that allows filtering of the instruments, and it looks something like this. The constructor takes in an instrument filter function. All it does is that this function has an interface that has a signature that it takes instrument definition types and returns a Boolean, whether to filter in or filter out that function. And this is quite a common pattern where we have a class which accepts a callback on in the constructor, and we want to save that function inside the class and invoke it at a later point in time. So in this case, this market data subscriber listens to the market data feed, and whenever a new instrument comes in, it invokes this function. If it filters in, it passes it on to the trading logic of the application. Otherwise, it just early exits. The important thing to note here is that we want this class to be fairly flexible, and the client should be able to pass any callable as long as it meets the function signature. So as long as it takes in a const ref to an instrument definition type and returns a Boolean, the client should be able to pass that function. So for example, in this case, the client is passing a free function, a lambda in this case, and a functor in this case. So we want it to be fairly flexible for the clients to use it. So let's consider some solutions of how this can be achieved in C++. The first thing you might come up with is, well, it's a fairly simple requirement. We want to store a function. Why not just use a function pointer? So in this case, I have a function pointer with the same signature in the constructor, and I store it as a function pointer. And on instrument definition, I just invoke that function pointer. Well, this looks good, and it has some advantages. This allows us to pass any free function, lambdas, or static member functions. But function pointers have their own disadvantages. Number one, the callables need to be stateless. So I cannot pass any lambda which captures some state. This pointers lack of value semantics. And whenever there's pointers, we need to deal with things like performing null checks. And I mean, there can always be a wrapper around it to do null check, to do a null check. But it is something to keep in mind. And I have those asterisks there because C++26 introduces std function ref, which can be used instead of raw function pointers. And it does allow some things like calling stateful lambdas, like lambdas which capture some state. I haven't looked into the implementation, but I believe it does type erasure under the hood as well. I'm not going to focus on how std function ref is implemented. Instead, I'll talk about std function. And I believe that will provide the building blocks for function ref. Now, if you take a step back, the requirement basically is that we have a common callable interface, that is, any function that takes in a const ref to an instrument definition type and returns a Boolean. And we want to accept any type which has this common callable interface. The first thing, like one of the first things that comes into my mind whenever I hear the phrase like common callable interface or like common interfaces is the use of inheritance and achieving runtime polymorphism using that. So let's consider a second solution using inheritance. Now I have this instrument definition callable class which has a pure virtual function, which has like this function called operator, which is a pure virtual function. It takes in instrument definition type and returns a Boolean. And I've defined two different concrete classes, equity filter and bond filter, and they override the virtual function, and they can have their own implementation. With this, my market data subscriber class can now just take a pointer to the base class, the instrument definition callable, and the client can provide any implementation of this instrument definition callable class. As long as the derived class inherits, I can use it and save it as a pointer to the base class. It is running off the slide. I could have used raw pointers here to ensure that it's within the box, but I know some of you would complain if I use raw pointers. So now I have this market data subscriber. It has like an equity market data subscriber or a bond market data subscriber, and it has different implementations, both derived from the base class. Well, this looks pretty good. It looks like almost like what we want. And inheritance does have some very lucrative benefits. One, it's a single concrete type holding different implementations. That's good. It achieves runtime polymorphism, and an important thing to notice that like the function can be reassigned during runtime. So if I want to reassign like change the equity filter function, I can do that at runtime by having like an assignment operator. But there are some downsides. Number one, now all callables are bound to be inherited by the interface. Number two, there's non-zero overhead at runtime. I wrote non-zero only because for most of the applications, a virtual function call overhead will not likely matter. But if your use cases where you want to like juice in every microsecond of latency, then a virtual function call might be some overhead. So that's something to keep in mind. It's not possible to pass third-party defined callables. For example, there's a library that provides a function with the same interface, like with the same signature, takes an instrument definition type, returns a Boolean. It's not really like possible or easy to use that because all the functions that you're using need to be inherited from the interface that's defined in your code, not that third-party library. And lastly, it still uses pointers. The client has to take care of lifetime management. So it's a bit clunky. It does not provide value semantics out of the way. Now, for completeness, there is another solution we can consider, which is using templates. So let's have a look at that. What you could like say is that, well, we need to store an invocable type. So as long as the function can be invoked using the instrument definition and like returns a Boolean, I should be able to use it and store it in my class. So you could simply template the market data subscriber on a type T, add some constraints to ensure that it's invocable, and I think I'm missing a copyable check as well here. So type T should be invocable and copyable, so I can store it in my class. And the constructor can simply have that template type T as a parameter, and store it inside the class. This looks pretty good. This would achieve what we want. The market data subscriber can be now created using an equity filter or bond filter. It takes in, because the concept only requires it to have an invocable type, it takes in basically anything that is invocable and stores it inside the class. So it definitely has some advantages. It accepts any suitable callable upon construction. Another thing to note is that it has zero overhead at runtime. It's just going to instantiate different templates at compile time for different callable types. So it's going to have zero overhead at runtime. But there are some downsides. Number one, with templates comes code bloat. As I mentioned, it's going to instantiate different templates for different types for different function spas. So there's going to be code bloat. But more importantly, it creates distinct types that are, for example, not easily stored inside a container. What we want is to have a common concrete type, not distinct types. And as soon as you have a templated type, which is like a distinct type, it becomes quite hard to store in a container. You can't simply store a list of market data subscribers in a vector. You might, if you know what all functions, what all types you're going to be instantiating this type with, you can have a variant of all of those and store it inside a vector, but it's not easy to deal with. So this is where a container like std function shines. With std function, you can simply use std function as the parameter, have the correct signature there, and now you should be able to pass a free function, a lambda, or a functor in this case. The critical thing to note here is that these different kinds of functions being passed to a common concrete type, the std function type, all these different types of functions being passed to that are completely unrelated. They're not bound by any sort of inheritance hierarchy or related by any means. They just implement the common interface, which is this function call operator, which has the expected signature. And somehow these completely unrelated types are assignable to a common concrete type, which is the std function. Okay, bit of a side note here. C++26 introduces std copyable function, which is meant to be a replacement of std function. I'm not going to go into, there's some nastiness which std copyable function addresses. I'm not going to go into the details of that, but you can check out the paper. I think it provides a pretty good example of why that is. So yeah, as I just noted, the important thing to note here is that these function types that are being assigned to a common concrete type are completely unrelated. And this is exactly what type erasure achieves. With type erasure, it hides the concrete type of an object behind a uniform interface and achieves runtime polymorphism without the need of inheritance or any sort of a common base class. And while I'm focusing on std function, this can be extended to any type erase class. Hope Sutter mentioned, sort of hinted towards type erasure in his talk on reflection earlier this week, and where he had a drawable type erase component, and then he had implementations like a square, a circle, and these don't need to be bound by any inheritance hierarchy. So as long as a square and a circle have a draw method implementation, you can use them and assign them to a common drawable class. So the big question is, how can these unrelated types be assigned to a common type? Std function in my case today, but any unrelated types having a common interface, how do we assign them to a common type? So let's take a step back, list down the requirements, and move on to how type erasure can be implemented and how it works under the hood. So there's basically two requirements of a function like container. It should be constructible from unrelated types, and it should have, all these types should have a common callable interface. Now, I mentioned before that as soon as I hear common callable interface, the first thing that comes into my mind is abstract classes with pure virtual functions. So let's go back to our inheritance solution and see what the pros and cons were. So So inheritance did provide some benefits. It was a single concrete type, unlike the templated solution. That was good. It implemented runtime polymorphism, and it bound all the types with a common callable interface, which is the second requirement. But it had drawbacks when it came to the first requirement. That is, it bound everything with a common base class, so the types could not be unrelated. So let's start off with trying to address these drawbacks. Let's start off with the second last, which is it's not possible to pass third-party defined callables. Now, here I have the same instrument filter concept that I had before. It's a base class with a pure virtual function. And my own library implements this isTalk filter class, which inherits from this base class and basically check if it's an equity. And for simplicity, for the rest of the slides, I have this filter instruments method, which I'm going to be using. It takes in a list of instruments, takes in a callback. It's going a bit over the slide, but basically it takes in, okay, when I scroll here, it's not going to reflect there. That's fine. Basically, it takes in a list of instruments and the callable that you want to pass, and it would return a list of filtered instruments. That's the example I'm going to be using for the rest of the slides. Now, this works fine as long as it's like my own library. The instrument filter concept is being defined by me, so any type inside my own library can inherit that, and I can use that. But the challenge is, what if there's a third-party library that's has this magical function, is $1 million stock, and I want to use this function to make $1 million, and how do I use it inside my library? Because this is not bound by the interface that's defined in my library. So let's try to address this. Well, the solution is pretty straightforward. What I need to do is simply create a new class which inherits from the base class, implements the function called operator, override, and calls the third-party function inside it. And that's it. I can now use third-party functions inside my library, and I simply need to now pass it as a pointer to the base class. While this works, it's a bit clunky because now the client needs to, my library needs to wrap every third-party function inside. I need a new class which inherits from the base class, implement the function called operator override. It's a bit clunky, a lot of code load there. So next, let's try to abstract this away from the client. Well, when I said it's not possible to pass third-party functions, I lied. It is possible to pass third-party functions, but it's just a bit cumbersome. Now, what do the isTalk filter function, which was defined in my library, and the is $1 million stock filter struct, which I had to define in order to use the third-party function, what do these have in common? Well, one, they both inherit from the common base class. Two, they both, as a result of the inheritance, they both have to override the virtual function defined. Only their implementation differs. Everything else remains the same. So let's try to come up with a generic class that inherits from this instrument filter concept base class, and which is constructible from any callable. So we can use templates here and try to combine templates and inheritance together to address this. Here I have this instrument filter model class, which is a templated class, but it inherits from a non-templated class, which is the instrument filter concept. And this instrument filter model class basically accepts any function type. We can always have some constraints on it, but for the sake of this example, it's unconstrained. It doesn't have any constraints. It simply has, it's simply a templated type, and the type is func type, and it takes in that as the constructor, and simply stores it inside the class as a data member. It also has, since it inherits from the filter concept class, it overrides the function call operator, takes in the instrument definition, returns a Boolean, and all it does is invoke this function that was passed to it during construction. So with this, I have a generic class now, which inherits from the base class, and you can pass it whatever you want as long as it's invocable by the instrument definition and returns a Boolean. And it's going to be able to, it will behave exactly the same as the different concrete classes I had, like the equity filter class or the bond filter class. This looks pretty good. Now, all I need to do is, instead of to use a third-party function like $stock, I don't have to create a new class anymore. All I need to do is use this templated class, instrument filter model, create an instance of it, and pass it to my filter instruments function. And my filter instrument functions takes in a list of instruments and the pointer to the base class. So this looks pretty good. We've abstracted away all the complexity from the client. It's still a bit clunky, wherein the client each time has to create a new instrument function, instrument filter model, and pass that. But looks like we're almost there with what we want to achieve. An important thing to note here is that with this instrument filter model, since it is templated and accepts any callable, my stock filter class, which was defined inside my own library, does not need to inherit from the base class as well. I can simply pass that functor and wrap it inside this instrument filter model and use it. So even the functions defined inside my own library now no longer need to be inherited. So let's recap. We have now we have mechanism such that filter instruments can now be called using any callable wrapped inside the instrument filter model. But there are some downsides. In particular, the client has to create a new object, pass in the pointer. It's a bit clunky. The client is still responsible for lifetime management since we're dealing with pointers. So let's try to address these. It's just some syntactic sugar to address these downsides. Now, all I have here is a new class struct function. Note that it's not templated, and I just moved the instrument filter concept, which was the base class before, and the instrument filter model, which was inheriting from this base class. I just moved those to be inner classes. So now I have this non-templated class struct function, two inner classes, and all I have to do is have a templated constructor which accepts basically any type, func type, wraps it inside this instrument filter model, and stores the pointer to the base class inside base class as a data member. So basically, the requirement was that I have these different functions, and the client needs to wrap them inside an instrument filter model and pass it to my function filter instrument definitions. But all I've done is I've created basically a wrapper for all of this. I've created this function type, which has a templated constructor. So give me anything. I'm going to try to wrap it in the function model for you and store it as a pointer to the base class. This also needs to provide the function call operator so that the client can invoke it. And that's pretty simple. All it does is invoke this operator on the pointers stored. A couple of interesting things to note. Now, any type can be passed to this function class, as long as it's invocable by instrument definition and returns a Boolean or something that can convert to Boolean, it can be passed. But this function class is not templated, so it does create a common concrete type. It does not instantiate different types. The other thing to note is that this function class, on the construction, it takes the actual type of what is passed to it. So it has the type information on construction, which is the func type. It wraps it around the function model, but it's only storing a pointer to the base class. So it kind of hides away the type that, the concrete type that you're passing to it. It hides away that in the filter model class, but it does not lose information of that type. And we'll see later why not losing information of the type is important for type safety in type erasure. All right, so now all we need to do is call filter instruments using any function, pass that into, simply create a function object, and it should be usable. This looks, this implementation is very close to, obviously very raw, but close to what a std move only function would look like. It's move only because I'm still using unique pointers in there. And as Scott Mears said in his book, More Effective C++, when in doubt, do as the ints do. So let's try to provide some value semantics to this class. In order to make the function copyable, all we need to do is use the prototype design pattern, provide a clone method inside, again, a pure virtual function inside the concept. The model inherits, the model overwrites that, and simply creates a new object of the same type, returns a pointer to the instrument filter concept, simply clones the current object, pretty straightforward. And now my function class in the copy constructor can simply call the clone method of the model. And since the model does have the type information, the model is templated on the concrete type. Okay, the outer class function has hidden away the type information, but the model does have the type information of the concrete object that was passed. So when we make a clone inside the model, it will clone the actual object which was passed to it. That's just one detail to know. And that's it. So in this example, I have an isEquity filter class which implements the function call operator. And you can see that when I create an object f1 and invoke it, it calls invoked it 1 times. Then I copy it. It's gonna print that the isEquity filter. I should have called it copy ctor instead of ctor because it's not a constructor, a copy constructor. But anyway, it calls the copy constructor of isEquity filter, so it looks like the clone is working correctly. And then it invokes it again, and I have this static counter, so it prints that it's invoked it 2 times. Let's recap what we've done so far. So filter instruments now can now be used by any callable. That's great. That's what we wanted to achieve. Pointers and lifetime management are abstracted away from the client. It provides value semantics, but there are still some implicit assumptions about the callable type. That's because it's got a templated constructor. You can pass anything to it. Having some constraints there would be nice. And lastly, it only works for this specific signature, which takes in an instrument constref to instrument definition and returns a Boolean. It would be nice to, since we're talking about std functions, it would be nice to have it work for any function signature. Well, that's just more template shenanigans. Here I have a function class which is templated on type T, and it has a specialization which has the type R as the return type and a periodic template arguments, args. Now I have added some constraints to the type that's passed to the constructor to ensure that it's invocable and returns the type R when it's invoked using the arguments. And now this is how my function call operator would look like. It takes the set of arguments args. If the function is not present, like that, it's a null pointer. It's gonna throw an exception, and if it's present, it's gonna invoke it using the arguments and return the type R. Everything else, like the model concept, remains the same. It's just more templates to make it closer to what a std function would look like. So again, the important thing to note here is that although I focused on std function and the usage of type erasure in standard library, you could create with very similar, with almost the same technique, which is the concept model hierarchy, your own type erase component. So you could just create a drawable type erase class, which has this concept, which implements, which has a pure virtual function called void draw, and then you can have a model that stores a pointer to the concept. And as long as the shapes implement this draw method, you can store it. You can wrap it inside a model and store it. And it's pretty elegant because now the types don't need to be bound by any sort of inheritance hierarchy. You can have completely unrelated types from third-party library or your own library, and have them be assignable to a common type. And it's basically what it's kind of what duck typing is, right? So you have completely unrelated types. As long as they meet this common callable interface, or any common interface that you define in your type-raised class, you're able to assign them to a common type and use them. So it's similar to how duck typing is in different languages like Python. Let's talk about cost of this type-raised class. Number one, it does some heap allocation on construction. Like if I go back, on construction, it makes, like, you pass a function, it creates a unique pointer, so it's doing some heap allocation here in the make unique call. Standard library has small buffer optimization. Like most implementations have this small buffer optimization which addresses this, and I'm going to speak about this soon. It also has some virtual function calls that have definitely some runtime cost. And there is, you could do manual virtual dispatch. I'm going to be, when I talk about std any towards the end of this talk, I'm going to show you another way of doing type erasure that does not have this cost of virtual function calls. So let's start off with small buffer optimization. This is a pretty standard technique where you have a stack allocated memory up to a certain size. If the size of the function is within certain threshold, like for example, in this case, I have the storage model type, which is a function model with a specific signature. I've just chosen this signature randomly, but the idea is that my threshold size up to which I store this function inside the stack, inside the pre-allocated stack buffer, is going to be up to the size of the storage model type. And any function that is that has a size higher than this will incur a heap allocation. On line 9, I have the pre-allocated buffer, which is a byte buffer. This is going to be on the stack. Alignment is important here, so that's a bit of a gotcha. Make sure that it's aligned correctly. The constructor is going to look something like this. It's pretty straightforward. If the type of the incoming function is smaller, is up to the threshold, do a placement new. Std construct that under hood would do a placement new on the storage, and if the size is greater than the threshold size, I've used new here, but basically you could just create a pointer using unique pointer, using make unique, and store it inside the class. Cloning it now becomes a bit different. Previously, the clone override was not taking any argument. It simply cloned the current object and returned it as a pointer to the base class. But now, when we are trying to clone it, it does need the access to the storage of where the object should be constructed if the size is within the threshold. So now, when on the copy constructor call, you can see that the current object passes its own storage to the clone method of the object it's trying to clone, and the target object checks that if the size is within the threshold, I'm going to construct it in place at the storage. Otherwise, it's going to create a new it's going to allocate a new function on the heap. And that's all I wanted to talk about std function. So let's now have a look at std any, which is another type-raised component in the standard library. As per our favorite website, CPP reference, std any is defined as the class any describes a type-safe container for single values of any copy constructible type. The important things to note here are, one, it says that it's a type-safe container. And two, it stores values of, it can store a value of any copy constructible type. So you could basically pass anything to a std any, and it's going to store it as long as it's copy constructible, but it's going to store it in a type-safe manner. So upon destruction, it's going to ensure that your object is destructed correctly. That's quite important for type erasure. The beauty of type erasure is that somehow it hides the type information from you, and yet it is completely type safe. An example of, like a dummy example of std any, here I'm assigning an integer to it, and you can assign it anything, and somehow it stores the type information of that. And you can print the type name. You can cast it back to the original type. Here I'm printing the type name. It prints int and casts it back to integer and prints that integer. I can reassign it to any other type. It reassigns it to a double here, and I can cast it back to a double. Here I reassign it to a Boolean, and if I try to cast it to a different type, like a double here, it's going to throw an exception. So having seen how type erasure works, and obviously I've hinted you that std any does type erasure under the hood, let's see how a std any can be implemented using the previous technique. Now, like any type erased component, like any type erased class, it's going to have a templated constructor. Any type erased implementation you do, it's going to start off with a templated constructor. And the reason is that the whole idea of type erasure is that you want it to be assignable, you want it to be constructible from completely unrelated types. How do you construct it using completely unrelated types? You have a templated constructor. So here I have a templated constructor. I've chosen similar terminology as before, and you'll see this in a lot of articles, the concept model hierarchy. It creates a new any model and stores it as a pointer to the concept. Pardon my usage of raw pointers here. Yeah, probably should have used unique pointers. All right, so I'm not going to go into too much details of this because we've seen this implementation before. Now, the common interface that I want to have within these unrelated types now is that the type information should be stored somewhere, and the client should be able to access the type information using the type method. So a bit different from what we've seen in std function, but on similar lines, there's a pure virtual function now to access the type information. Std type index is just a copyable wrapper over type info. So the model inherits from the concept, similar to what we've seen before. The important thing here, again, being that the model does have the information of the concrete type. So it's the model that's going to be doing any type-specific, like the concrete type-specific things. Here, it simply gets the type ID of the incoming type and stores it inside the class. And all I now need to do is give the client's access to this public member function called type, and they can and simply invoke that using the pointer I have in the class. And that's it. I mean, we've seen this implementation before. It's pretty similar to what we did before in std function. But next, what I want to show you is implementation of std function without using virtual function calls. So let's have a look. And I believe std any is implemented like this in most implementations. Now, so I've said previously that the model has the type information, but obviously the class, like any class or the function class, does have the type information as well at the constructor. It's just that after construction, that type information is hidden inside the model, and the class does not have access to it. The class that you're constructing does not have access to it. But in this case, for example, the class any does have access to the type information in the constructor. And to store the type is pretty simple. Here I have private data member type, which is mtype. It stores the type information of the incoming type. And yeah, at construction, it has the type information. So all it needs to do is store that store that in the data member mtype. Well, this looks pretty good. This was pretty easy. Like, why do all this type erasure shenanigans with concept model hierarchy and stuff like that? This works, but there is an important detail to note that std any has to be type safe. So the challenge now is that in the destructor, we do have the type information in std type index, but I'm storing it as a void pointer in std any. So I probably missed that part. But basically what the constructor is doing is that the class stores a void pointer to the value, and the constructor simply creates a new object on the heap of the same type, and stores it as a void pointer to the type. And separately, it stores the type information in type index, in a std type index type. So now my class has a void pointer. The challenge is, how do I delete the void pointer? I need the correct type, like the concrete type, in order to delete it correctly. What we could do is that during the construction, the type information is there. So we could store a std function in the class, which we could create a function which is a deleter. And at the time of creating this function, I do have the type information. This function takes a void pointer as the argument, static casts the pointer back to the concrete type, and simply calls the delete on it. And this class is now going to store this function inside it, and on destruction, it invokes this function. So again, we've taken a concrete type, hidden the information of it, like the class allocates the type on the heap, and allocates a new object on the heap, stores it as a void pointer. This void pointer, as soon as we cast it to a void pointer, it's lost the type information. But it also stores a deleter function, which it uses to delete it. And at the construction of this deleter function, it does have the concrete type information. And this is how we can achieve type erasure without any virtual function calls. To recap, type erasure enables the use of unrelated types with a uniform interface. This is superior to using inheritance, because inheritance bounds the types by an inheritance hierarchy. It does not require inheritance and reduces dependencies between various types. It is prevalent in the standard library. As you see, we saw the example of std function, std any. I believe I've got some time to go over std shared pointer as well, just to give you another taste of type erasure. So I'm gonna discuss that soon. And it achieves duck typing, which is common in other languages, as long as all it requires is that is the object to have a common interface, and as long as you pass that object, you can use it with your type erased class type. Now, I do have a few minutes, so I'll go on to the bonus slides, which I know everyone loves to see some bonus slides. So I'm going to talk about shared pointer and type safety, and how shared pointer does type erasure under the hood. So consider this noisy foo class. All it does is it prints to standard output on construction and destruction. And although you shouldn't have this in production code, but say you create an object of that class and assign it to a void pointer, and at some point later you try to delete it. What's going to happen? Any guesses about this code? It's going to delete it correctly. Well, this is not going to compile. Deleting a void pointer is undefined. The warning in GCC, warning in Clang 19, and if you have warning as errors enabled, it's not going to compile. The standard library says that an object cannot be deleted using a pointer of type void star, because void is not an object type. So how do we delete this void pointer correctly? Like say you do have a void pointer. How do we delete it correctly? We've seen the solution already in the implementation of std_any. At the time of the construction, at the time you created this void pointer, you did have the knowledge of the concrete type. So just have a lambda as a deleter and invoke it at a later point. Let's say you try to create a unique pointer, so you're trying to create a unique pointer of this object type noisy foo and store it as a pointer to void. Well, we were able to do line 7 compiles here. So we were able to create a pointer. We were able to create an object of type noisy foo and store it as a pointer to void. What about this? Any guesses what happens here in this code? Yeah, that's right. This is not going to compile. Again, different styles of saying the same thing. Can't delete a pointer to incomplete type. And this doesn't compile because unique pointer actually has 2 template arguments, if you see the signature. It has the type t, which is the type to the pointer, and then it has a deleter. And the deleter is defaulted to default delete of the type that you pass to it. So in this case, it's going to try to default. It's going to have the deleter as the default delete of type void, and that's not defined. So default delete of type void is not defined. So what we could do here is that since the unique pointer does take a deleter as the second template argument, you can simply, again, create a lambda and pass that as a deleter. But now I have a void pointer that points to this class noisy foo. And since this is a void pointer, I should be able to do something like this, where I have another class noisy bar. And I want to reassign this pointer to another void pointer of this different class. This seems like pretty doable. Well, I have 2 void pointers. I'm just trying to reassign one void pointer to point to another void pointer. Sure, they're pointing to different objects, but it should be able to handle that. But this is not allowed. And the reason is that, well, these are 2 different concrete types. Since you have a deleter to the type foo here, and then you have a deleter to the type noisy bar here, you're trying to reassign to a unique pointer to one concrete type. You're trying to reassign to a completely different concrete type. What about this? Now, all I've done is replace the unique pointer with shared pointer. Any guesses? Completely fine. There we go. Chris knows it. All right. So this works great. I create a pointer previously. So I've created a pointer ptr which points to an object of type noisy foo. It constructs that. Then I reassign it to a pointer to an object of type noisy bar, and it's able to reassign it. So somehow it works on shared pointer, but it did not work on unique pointer. And unique pointer was creating two different concrete types. And if I look at the signature of a shared signature of a unique pointer and a shared pointer, unique pointer has 2 template arguments, whereas shared pointer only has a single one. So how is shared pointer somehow able to reassign it and destruct the type correctly? So when I reassign a void pointer which points to an object of type noisy foo, when I reassign it to an object of type noisy bar, shared pointer is able to destruct foo correctly. So somehow it's storing despite storing it as a void pointer, it's saving the type information of the actual object passed. And this is because shared pointer uses type erasure under the hood as well. So unique pointer t only stores the template type information. Shared pointer stores both the template type information, type t that you're passing, and the object type information. That is the object you passed to it during construction. And shared pointer uses type erasure to call the correct destructor. And this is where type safety comes in, like as we saw in std any and shared pointer. So high-level overview of how a shared pointer is usually implemented under the hood. It has a pointer to type t, which is the template type you're passing. It stores this pointer to type t stores an object of this type, and then it has a pointer to the control block. This control block has various things. It has a reference count, a week count, and some other data. What we are concerned here is about is the custom deleter. That's what we care about for this section. So it has a pointer to the object, which is of type t, and a pointer to some control block, stores the reference count, some other stuff, and a custom deleter. Let's see. I'm just going to go over like very high overview of how it works. But you can imagine that what we've seen before, how a type-raised class works, you can imagine it works very similarly. So the shared pointer has two constructors to start off with. Like it has a lot of constructors, but two of them are here. The first constructor, line 5 and 6, you can see that it has a templated, like the constructor is templated itself. So the shared pointer, the class is templated on type t, but the constructor is templated as well. And as we saw previously, the first thing, like when you go on implementing a type-raised class, the first thing you do is have a templated constructor. So you could pass an object of different type y to a shared pointer as long as it's constructible, as long as the pointer to y can be converted to a pointer to type t. So what this constructor does is this constructor calls, like it's a delegating constructor. It calls the other constructor. You can see the second constructor, line 10 and 11. That takes an explicit deleter. But I guess the constructor we're concerned about is on the first constructor. And the important thing to note here is that the default deleter is now a deleter to type y, which is the actual object. In a unique pointer, the default deleter was the deleter to the type that you were passing as the template parameter. So that would be default deleter of type t. But in a shared pointer, it's a default deleter of type y, which is the actual object type. That is how it's able to store or like able to invoke the correct deleter. So this delegates to the second constructor. And now the challenge becomes that we have the second constructor, which takes in a pointer to y. That's easy to store. Like the class has a member function, a pointer to t, and we already have a constraint that the pointer to y should be convertible to a pointer to t. So that's easy to store. But how do we store this deleter now? This deleter is again a templated type. Like the constructor is templated. So how do we store this deleter? And going back to the concept model hierarchy, this is what a very simple control block would look like. There's a control block base, which is the concept. It stores like the ref count, but more importantly, it has a virtual destructor. And then I have this control block, which is similar to a model which we saw previously. It's templated on the object type, the type y, and the deleter. And in the destructor, it calls it stores the deleter and it calls the correct deleter on destruction. So you can imagine, like I'm not going to go into the details, but you can imagine that shared pointer wraps the deleter into this control block and stores a pointer to the control block base inside the class. And that's it. So if you take anything out of this session, I hope that you have a better intuition of how type erasure works under the hood, and you have an appreciation of how type erasure differs from inheritance and can be superior in some cases. Thank you. If there's no question, either I did a really bad job or I did a really good job. And I'd like to think I did the latter. So thank you so much, everyone. Cheers.